nice little problem that that we have been working on, say, for the last year or so, together with my colleagues Tobias Breiten from Technical University of Berlin, Lara Neureiter from BTU Cottbus-Senftenberg, and Upanshu Sharma from Freie Universität and BTU. And so I will first provide a little bit of background, because I mean, even though this is a UQ seminar, I don't assume that everybody is familiar with the Langevin equation and Markov chain Monte Carlo, but feel free to interrupt me if everything I tell you is well known for you. Okay, so what is the problem? So okay, let me try to get rid of this here. Just a second. I want to minimize the videos. Okay, so if you want to approximate integrals by Monte Carlo, so basically you're looking at something like this, where you have an integral over a function g of x with respect to some measure mu. And if mu is a probability measure, you can think of this as an expectation, and you can approximate.
I still only see the title page. Is that true for everyone, or?
No, I should be on the next slide already.
No, I see only the title page.
No, I see the second one.
That's interesting. Okay, let's try once more. Do you still see the title page, or?
No, I see the second one.
Yeah.
And now? Do you see another one now?
We see motivation.
No, it gets stuck there.
It's stuck there. That's weird. Okay, so maybe I can try this.
Now it flipped.
This way, yeah. So I will. So apparently the full screen mode doesn't work. Okay, let's try this. So if you approximate integrals by Monte Carlo, you think of the integral as an expectation, and you use the law of large numbers to approximate the expectation by a mean. So you have some, well, either independent, so IID random variables, or weakly dependent random variables that are distributed according to some measure mu, and you take the mean of this function g of x at the random samples, and that gives you an unbiased estimate of your integral or your expectation. This is something that is very powerful, so because you can approximate almost any reasonable function by this method, if you're able to generate data from your target measure mu. And so this is sometimes tricky when you have distributions mu that have a feature that is called multimodality. So if you have a probability density function with multiple modes, then the sampling method typically has difficulties to flip between the modes. So it's very simple to sample a single mode, but once you have to switch to another mode, the Monte Carlo sampling method may get trapped. And so you may ask, hey, why do I want to do Monte Carlo if this is such a big problem for complicated distributions? Well, the answer is you do Monte Carlo because you can beat the curse of dimensionality with Monte Carlo. So if you think of approximating your integral by a quadrature method, you can do this in dimension 1 using a grid. You can do it in dimension 2 using a 2-dimensional grid. You can even do it in dimension 3, but you see that the number of grid points you have to use in order to get a reasonable approximation of your integral grows exponentially with the dimension of the problem. And if you think of problems like in Monte Carlo, where you compute expectations or integrals over thousands of degrees of freedom, then doing any quadrature-based approximation is not an option. The good thing about Monte Carlo is that the typical convergence rate that you can measure using the central limit theorem is more or less independent of the dimension of the system. So if you look at this expression here, so you take the difference from your estimator, so the mean, and the expected value you want to compute, and you scale by square root n, where n is the number of data points you're using, and by the central limit theorem, this quantity converges to a Gaussian random variable with mean 0 and variance sigma g squared. And the sigma g squared is not completely independent of the dimension of the system, but it's only weakly dependent on the dimension. So normally you can get very good bounds on this that don't blow up as the dimension of the problem becomes large. So this is why we are doing Monte Carlo or Markov chain Monte Carlo, which is a variant where we use some stochastic dynamics to generate data from this distribution, target distribution mu. And I quickly want to explain the idea, even though I assume that most of you are familiar with Markov chain Monte Carlo. So the idea simply is now that we consider a Markov process X that depends upon some parameter epsilon, where epsilon will be the noise or the temperature in the system later on. And I assume that X has a unique invariant probability measure mu that has full support. And so this means I mean, in many cases, it means I can write down a density that is everywhere positive. And invariant measure means if I initialize my Markov process with this measure mu, then for any time t, the distribution of this process will have the same distribution mu. And so this is not yet an algorithm that tells me how to compute data that is distributed according to mu, but the idea is to exploit ergodicity of the process and generate a very, very long realization of this Markov process. And if the Markov process is ergodic with respect to this measure mu or mu epsilon, then we can compute the expectation over mu as an expectation over this long realization that we have generated. So we can replace this, so what physicists call ensemble average, as a time average over this function g of x along the realization. And this is an almost true equality that holds for any or almost any initial condition and any reasonable function g. Okay, so that's the idea of Monte Carlo or Markov chain Monte Carlo. And a very, very popular system that people have studied a lot is the so-called overdamped Langevin equation. I will speak about the underdamped Langevin equation today, which is a slightly different equation that will come next. But the overdamped Langevin equation is very popular because it has a very nice and straightforward interpretation, and it also has nice mathematical properties if you want to analyze speed of convergence of these Monte Carlo schemes. So the idea is that if we have some function v, and this function v will be related to the target measure or the density of this target measure by this relation here. So my density can be expressed as an exponential of minus v over epsilon, where epsilon is a parameter that we can freely choose, or in some cases it's given, sometimes we can choose it. And so this Langevin dynamics is essentially a gradient flow in this function v, but it's perturbed by white noise. So this is, well, the simplest first order stochastic differential equation we can write down for this system. And if this measure rho of this measure mu and the function v have certain properties, then this will be the unique invariant measure, and it will be ergodic. So this means that any sufficiently long trajectory samples from this measure. So, so this is an example here. So this plot shows a density rho that has two modes. And when you generate a long trajectory, you see, so if you start in the left mode, for example, the dynamics will spend a fairly long time in this mode before you eventually see a transition to the other mode. And then the system is able to sample the right mode before it goes back again to the left mode. And these transitions are rare, and they are rare compared to the typical timescale in which you integrate this dynamic. So if you think of this equation for this only one-dimensional simple double well potential v, so this is the function v here, then you have to do something like almost 1 million or 500,000 time steps before you see a single transition from the left well to the right well, or from the left mode to the right mode. And so this is particularly a problem when epsilon is small, which happens often in applications, because when epsilon is small, you see what is called a concentration of measure phenomenon. So if, as in this case, v has a unique global minimum, so which will be this left well here, then as you send epsilon to 0, the invariant measure will concentrate in this minimum, and it will eventually weakly converge to a Dirac measure located at the global minimum of this function v. And so this shows already that the system is likely to get trapped in these very deep lying minima. And in fact, you can show that the convergence for these Monte Carlo schemes is very poor when epsilon is small. So this means when the noise, the perturbation by the noise of the system is very small. And I will come back to this point in a minute. So these the speeds of convergence can be quantified. So what one can show is that if you study this Langevin dynamics, so this overdamped Langevin dynamics, and you ask at which rate does the system converge to its invariant measure, to the ergodic invariant measure, and if you measure this speed of convergence, say in the total variation norm, then you can show that this discrepancy between the time t distribution and the invariant measure is exponentially small in some with some rate minus lambda epsilon. So epsilon is again the noise level, and lambda is related to is a property of the measure. It's actually independent of the dynamics, but it can be related to the particular dynamics because this lambda is the log Sobolev constant associated with this probability measure mu. But you can show that this lambda can be bounded from above by the spectral gap of the infinitesimal generator of this Markov process. So there's a differential operator associated with this overdamped Langevin equation, and this differential operator has eigenvalues in certain cases, and the principal eigenvalue that is closest to 0, so these eigenvalues are real, so this is something one can show. The one that is closest to real to 0 gives an upper bound, so gives an upper bound, or the negative of this eigenvalue is an upper bound of this convergence rate lambda. And so this means, and one can show that this upper bound is exponentially small in the ratio of the energy barrier. So this is the barrier one has to cross in order to leave the lowest minimum, and the noise level epsilon. So these numbers are all very close to 0. This means that the convergence to the stationary measure is extremely poor whenever epsilon is small. And you can see it here in these simulations. So for the blue plot, so this is the simulation with the same double well function v for a small temperature, and you see this metastability effect, so you get trapped in the lowest well. Whereas if you simulate this for a larger value of epsilon, so the invariant measure has the density which is shown in red here, then the transitions between the left and the right well are much more often. Okay. So in this talk, I will use 2 points of view to characterize this this Markov chain Monte Carlo method. And the first one, and I explain it again for this overdamped Langevin equation. The first characterization is in terms of the stochastic differential equation. So I will directly look at the stochastic process that is governed by this stochastic differential equation, and I assume that my initial conditions are drawn from some distribution. And the alternative point of view is to look at the evolution of the density. So if I ask what is the distribution of my process x at time t, given that I have started from a distribution f naught at time 0, then this distribution is governed by the Fokker-Planck equation, which is a linear parabolic PDE that describes the evolution of this density. So I will represent sometimes this linear Fokker-Planck equation in terms of this operator A, which is just the L2 adjoint of this infinitesimal generator, which is the operator that has spectral gap, which determines the speed of convergence to this invariant measure. And so I will use both points of view interchangeably, more or less, to say something meaningful about this underdamped underdamped Langevin equation that I will present in a minute. Okay. So the simple relation between these two is, I mean, here I've written it again. So if you ask what is the probability that the process at time t is in some set A, then I can, of course, characterize or equally determine this probability by integrating my density at time t over the measure, over the set A. Okay, just to give you an example why these things with small epsilon and many local minima are important, and molecular dynamics is one example where all these problems come together. So when people sample the energy landscapes of a molecule, they are interested in computing this e to the minus v over epsilon density, where v is a complicated function that has many local minima. And so this is now a two-dimensional projection of the energy landscape or the interaction potential of a Lennard-Jones 38 cluster. So that's a molecule with 38 atoms. Each one can move in 3D or 6D if you add velocities or momenta to it. And that's a 2D projection onto a set of collective variables. And you see that there are many fairly deep local minima. And it is important when you want to study, for example, isomeric transitions or conformational transitions in these molecules, that you're able to visit all these local minima and leave these local minima again. So once you get trapped in one of these local minima, you also want to leave it at some point in order to visit the next local minimum. And so this is important because all these local minima correspond to modes of the probability distribution that you want to sample at the end. And typically in these applications, so what determines the speed of convergence is this ratio between delta V and epsilon, where delta V is this energy barrier of the energy minimum that I have to leave in order to reach the next one. And so typically this ratio is fairly large. So this means that epsilon, or the noise level, is small compared to the typical energy barrier in my system. Okay. So this is now part one of the take-home message. So the most important thing is yet to come. But what you should keep in mind is that this Markov chain Monte Carlo is simply a tool to sample from complicated multimodal probability distributions using some Markov process that weakly converges to this measure. And I want to compute these expectations by exploiting ergodicity, which means I average over one very long realization of my process. Typically, so people in molecular dynamics or statistical mechanics, they like this Langevin equation because it has a nice physical interpretation, as a gradient flow. It also has nice mathematical properties, because you can also interpret the Fokker-Planck equation as a gradient flow in some sense. And people in statistics use this dynamics as well, because there's a simple relation between the target measure mu, or its density rho, and the function v I have to put in this Langevin dynamics on this Langevin equation in order to be able to sample from this density. Because I can simply take the logarithm of this rho, take the gradient, and off you go. So you can plug this into your discretization scheme and generate trajectories that will follow the distribution rho if you ignore discretization errors at the moment. So the difficulty in practice is that in many interesting situations, the epsilon will be small, so the noise will be small. And this means that the t you need to sample, so the time you need to sample the dynamics will be very long. So we have sort of two limits that are involved in this game. One is the small noise limit, and the other one is the long time limit. And I will take a look at these two limits for the underdamped Langevin equation in more detail. Okay, so that's the intermediate summary, and now comes the main part of the talk. So I will now introduce another model, which is this underdamped Langevin equation, and explain the invariant measure and some of the properties for this Langevin equation. And then I will play around with the temperature, because I've talked about this small noise problem. And the question is whether in this underdamped Langevin equation we can play around with the noise and make the noise larger, but still sampling from the same probability measure. And so this is something that is possible for the underdamped Langevin equation. It's not easily possible for the overdamped equation, but the underdamped Langevin equation has some features that allow us to play around with the noise level. Okay, so what's the underdamped Langevin equation? The underdamped Langevin equation is, well, sort of a second order stochastic differential equation, or a degenerate stochastic differential equation that basically has the form of a Hamiltonian system that is perturbed by friction and noise. And I will show you what I mean by this on the next slide. So I assume, again, I have some function v, which is a smooth and well, sufficiently growing potential function that is bounded from below. And I have some friction matrix gamma, which is a symmetric positive definite matrix. And I have some noise coefficient sigma, which also is some matrix. And what one can show, and this relation will be important in the following, is that this dynamics has a unique invariant measure, and it's also an ergodic invariant measure, which is given by a density. So that's now a Lebesgue density in xy that is given by e to the minus beta h, where h is the Hamiltonian or total energy of the system, so the sum of kinetic and potential energy. And this is the density if and only if the friction and the noise coefficient satisfy this fluctuation dissipation relation. So if the friction is proportional to the noise covariance, basically. And the factor of proportionality determines this scalar beta. Okay, so if and only if this relation is satisfied, then this is the density of the invariant measure. Okay, so why did I say this is some variant of Hamiltonian dynamics? If you're familiar with stochastic differential equations, then this will be nothing new to you. But if you're not, just look at the orange part of the equation and divide by dt, and then you will recover a Hamiltonian system with this Hamiltonian. So it's basically the typical skew symmetric form of a Hamiltonian system with this Hamiltonian and potential energy V. And we perturb this Hamiltonian system by a linear friction force. So this causes dissipation because of the minus here, and because gamma is positive definite. And in order to compensate for the friction, because the Hamiltonian system would preserve energy, with the friction it would lose energy. In order to compensate for this loss of energy, I pump in energy by adding noise. And if friction and noise satisfy this fluctuation dissipation relation, then on average the energy will be preserved. And because the deterministic Hamiltonian system without friction would preserve the energy exactly, so it would in particular preserve e to the minus beta h, turns out that the stochastic system also preserves e to the minus beta h, but that's the only conserved quantity in this case. So that's because that's really the unique invariant measure. So this is very different from the deterministic Hamiltonian case, where any function of the Hamiltonian would be an invariant. But so this is really a special feature of this Langevin dynamics. All right, so so I quickly want to mention relevant work done by others on the underdamped Langevin equation. So from a mathematical point of view, this underdamped Langevin equation is not so nice because the operator that appears in the Fokker-Planck equation is not self-adjoint. So one can show that in this case, the infinitesimal generator is a self-adjoint operator, and therefore you know a lot about its spectrum, and you have functional inequalities available that you could use to study the speed of convergence. And all this is very different for this underdamped Langevin equation because the noise is degenerate, so it's not a uniformly elliptic operator. Nevertheless, the operator has nice properties, and there are very sophisticated PDE analysis works by very bright people who have studied the speed of convergence for this underdamped Langevin equation. So these involve PDE approaches by Heira, Paviotis, and the French community, and also Anton Arnold. And there are purely probabilistic approaches, also by Mattingly and Stewart, and Eberle and Zimmer and Rebellet. Then there's work on numerics for these methods, because it's not so trivial to preserve the invariant measure when you discretize the dynamics. You have to correct for the discretization error. And there are also variants, works on extensions of these models where the friction is not just a linear friction term, but something that involves delay of the system. So there are also non-Markovian variants for this for this Langevin equation that have been studied by various people. I just want to mention it. If you have specific questions about about these results, we can discuss it afterwards. I just want to mention it for the sake of completeness, even though this is not a complete list, probably. Okay, so I said that one problem with sampling the distribution using Markov chain Monte Carlo is the multimodality in the distribution, and this has to do with the fact that we have small noise in our system, because the smaller the noise, the more pronounced will be the modes of my probability distribution. So what can we do in order to solve this problem? Well, I would say we solved it, but we have some idea at least. And see, the idea now is the following. So if we assume that the small noise is a problem in the equation, then we could try to increase the noise level by, well, changing the diffusion coefficient, and we change the diffusion coefficient in such a way that we make the diffusion larger. But then we will not sample from the correct invariant measure because of this fluctuation dissipation relation that tells us exactly what happens if we increase the noise coefficient or the noise level. And so what we do is we change the diffusion coefficient to another diffusion coefficient. Or, well, in fact, it's the same sigma, but it satisfies another fluctuation dissipation relation at another temperature. And in order to compensate for this change in the diffusion coefficient, we add a control force that I call sigma times u. So it's scaled in the same way as the noise for technical reasons, but u is a control force that has to be chosen in such a way that even though I simulate my Langevin dynamics at a higher temperature or a higher noise level, I sample from the correct target invariant measure. And I will come back to, so I will explain to you in a minute how one can determine which U does the right job. But at the moment, the point is, so I change the diffusion coefficient in such a way that the new diffusion coefficient satisfies the fluctuation dissipation relation, but at a higher temperature. So beta bar is what's called an inverse temperature. So this is 1 over epsilon in the previous overdamped Langevin equation. So this beta bar is less than beta. So this means the temperature is higher. And so this will reduce the metastability or the multimodality in my distribution and make everything somehow more flat. And I call beta the target temperature. So this is the small temperature that I had originally, and beta bar is the simulation temperature, which corresponds to the higher temperature I want to use to the Monte Carlo simulation. What you can see immediately is, of course, if I set u equal to 0, so if I don't use control, then I would sample from the wrong invariant measure, because I would sample from the invariant measure at the simulation temperature beta bar, but not the target temperature beta. Okay, so let's think about how to use the control in order to restore the correct invariant measure. And the following can be shown, and that's both a necessary and sufficient condition. So if we assume that our simulation temperature is lower than the target temperature, and so I think this should be, no, that's correct. Yes, so the simulation temperature is higher than the target temperature because this is 1 over temperature, and we make the ansatz for the control that the control is a linear forcing in my state variable y for some matrix B. Then the target measure mu infinity is the unique invariant measure if and only if this matrix B that appears in my control satisfies this matrix inequality. And what you see immediately, if the simulation temperature equals the target temperature, then so the right hand side disappears, and so the matrix B has to solve this this matrix inequality with right hand side being equal to 0. However, if my simulation temperature is higher than the target temperature, then this matrix on the right hand side will be negative definite, and so the B introduces some kind of friction force to the system, so it compensates the higher simulation temperature. And this matrix equality is actually an interesting one. So it looks a little bit like a Lyapunov equation that appears, for example, when you compute the covariance matrix of a Gaussian process or Gaussian linear SDE. You will see equations of this form, but so this is slightly different in this case. So this is not exactly a Lyapunov equation because of the the form on the left-hand side of the equation. This is what is called a T-Sylvester equation. And also, unlike Lyapunov equations, these T-Sylvester equations don't have unique solutions in general. And so what one can show is that any matrix of this form is a solution to this T-Sylvester equation. So the difference is that Lyapunov equations have symmetric solutions, and this T-Sylvester equation does not have a symmetric solution necessarily. And so you can show that any solution of this form that has this additional term sigma h, where h is any skew-symmetric matrix of the right size, satisfies this equation. So we have some freedom in choosing the control. And so, this means we have now necessary and sufficient conditions that tell us under which conditions the control preserves the right invariant measure, but we still have some non-uniqueness in the control. So we have a whole family of controls that preserves the right measure. And the question now is, which one is the best one? So which one to pick? And so the aim now is to identify a unique control or an optimal control, so that, of course, we sample from the correct invariant measure. So we're looking in the family of controls that satisfies this lemma, but we want to pick the control in such a way that the difference between the original measure of the uncontrolled dynamics and the controlled dynamics is as small as possible. So this means I want to use the control in order to mimic the dynamics of my original Langevin equation. So if you think of it from the perspective of statistical physics, I want to have a dynamics that is controlled but generates something like a close to equilibrium situation. And I measure the discrepancy between the original dynamics, which is now expressed in terms of the solution to the Fokker-Planck equation, and my control dynamics using relative entropies or Kullback-Leibler divergences. So I define the Kullback-Leibler divergence between two densities, or can also write it down for measures, eta and rho, as this expression here, assuming that rho is positive, or that the two measures are absolutely continuous with respect to another. And then I can unambiguously define this expression, and I want to choose a control such that this relative entropy between the uncontrolled density and the controlled density is as small as possible. So that's the idea. Now you could ask, and so this relates to a remark that Raoul made at the beginning. So so this looks like a change of measure, and indeed, so the control is able to change the measure, but on the other hand, I want to preserve the invariant measure. However, so if you think of classical change of measure techniques that you can use for stochastic differential equations like Girsanoff transformations and so on and so forth, and you can also compute the relative entropy in this case, then you never touch the diffusion coefficient. So the difference here really is that we have changed the diffusion, and because we have changed the diffusion using Girsanoff transformations or Girsanov's theorem is not an option, because so on the path space, the two measures of the uncontrolled SDE and the controlled SDEs are mutually singular. So they are difference, and the relative entropy will be equal to plus infinity, no matter what. So no matter which control we choose. So because the diffusion coefficient has been changed, there's no way to compare the two distributions on the space of trajectories or on the path space. what we can do, however, is to compare the finite time marginals, which are the solutions to the Fokker-Planck equations. And this is something we can do. So because the relative entropy is well defined, even if we change the diffusion coefficient, the two Fokker-Planck equations have nice solutions. And so the question is, yes.
Yes, just going back to the previous slide, I think you were making the case for preserving the invariant marginal, right? I mean, the infinite. I mean, the infinite limit when time goes to infinity.
Yes.
But now you introduce this marginals at time t. So how do you make the connection between the two? Because if you make a control that is trying to mimic the infinite time or a given marginal, at a given time, is one thing, but at another time that may be different. So is this transient something that you want to preserve, or is just the introduction of the Kullback library in this slide?
So I think so we know that as t goes to infinity, we preserve the invariant measure. So if t is large, this Kullback-Leibler divergence will go to 0 anyway, right? So the question is, how can we make sure that this Kullback-Leibler divergence goes to 0 as quickly as possible? So in fact, so what I said was maybe a bit misleading. So at the end, we will initialize the uncontrolled dynamics in the invariant distribution. So it will have the target distribution for any t, and we want to control the other Langevin equation so that this distribution is reached as quickly as possible.
Okay.
So I mean, in this sense, you're right. We want to control the transient behavior of the dynamics, because for t to infinity, we know what's going to happen anyway.
Yeah, because I mean, if one wants to kind of, sometimes one will average over time, say this functional with some weight or something like that, and that would be the functional to minimize.
Actually, I mean, yes. I mean, I will now explain how one can quantify this relative entropy, and at the end we will indeed average over time.
Okay, good. Then I understand. Thank you. Thank you very much.
Okay, so let me quickly explain to you how we can control the relative entropy. So what one can show is, and this is partly based on work by my collaborator Upanshu Sharma, was part of his PhD thesis. So if we take the time derivative of the relative entropy, and keep in mind that both eta and rho solve some Fokker-Planck equation related to the controlled or uncontrolled dynamics, and we can basically use chain rule to compute these derivatives. And it turns out that you can express the entropy production rate, or the rate of change of the Kullback-Leibler divergence, by two terms. One is related to the Fisher information between eta and rho, or it's a relative Fisher information because it's the weighted form. And the second term is a quadratic functional of this form, which is related to some rate function from large deviations theory. Basically, so it says, so if you consider your Fokker-Planck equation, the one you want to solve, but you plug in the wrong density, how large is the error that you make, or how large is the entropy production related to this wrong solution in the right Fokker-Planck equation? And what we do now is we drop the first term, because it's it's positive anyway, but so this inequality holds for any tau greater than 0, and if we set tau equal to 1, the Fisher information term does not play a role because we cannot control this term anyway. And what remains is this quadratic term that depends on u. So this term explicitly depends on the control u, and it also depends on the difference in the diffusion coefficients. And so this is now a relatively explicit characterization of our, it's an upper bound, but it's a relatively explicit characterization of the entropy production rate in terms of the control that we use and the difference in the diffusion coefficients. And so if we minimize, so we can minimize, as Raoul said, a time averaged version of this this entropy production rate. So here I integrated this expression over time and divided by time again. So this is a time averaged version of this entropy production rate, or you can think of it as the asymptotic entropy production rate. And then it turns out that if we minimize this expression over U from the class of admissible controls that preserve the right invariant measure, then the optimal control U is the one that has a symmetric B matrix. So the optimal control approach really picks the matrix B that is symmetric again. So the matrix, so sigma times B will be symmetric. And because sigma times B is the term that appears in the control force. And so this means, again, that we get a new fluctuation dissipation relation, which now involves the extra friction term sigma times B. And this new control force now satisfies the fluctuation dissipation relation at the correct target temperature. So that's somehow circular, right? We have increased the noise, then asked which control does compensate for the noise, and it turns out the optimal control is the one that restores basically the old fluctuation dissipation relation. But of course, we have some more freedom to play around with these matrices here now. And still, we have the freedom to choose the diffusion coefficient in a different way. So it gives us more degrees of freedom than we had originally. And now the question is, okay, sorry for the German expression. So is it always a good idea to increase the temperature, so the diffusion coefficient, to make it very large and then compensate for it by adding this additional friction force? And so we have asked this question because at the end it turns out that the Langevin dynamics basically depends only on the temperature ratio beta over beta bar. So this is the ratio of inverse target temperature and simulation temperature, and we are interested in, so if we want to make the simulation temperature very large, so this means we want to send this ratio to infinity. And we can do it in two ways. We can either say, okay, I fix my target temperature and make the simulation temperature very high, which means I send beta bar to 0. Or if I just want to send this ratio to infinity, I could also say, well, I can keep my simulation temperature fixed and send the target temperature to 0. We know what is happening then, because if we do this, we know that our dynamics will converge to a global minimum of the energy landscape, if the energy landscape has a global minimum, and otherwise it will converge to a combination of the local minima, or of the lowest minima. And so we've studied these two scenarios, so these two limits, beta to 0, keeping beta, beta bar to 0, keeping beta fixed, and beta to infinity, keeping beta bar fixed. And I think I will spare you the details of this calculation, because that's actually quite standard perturbation and multiscale analysis. So I just want to show you the equation. So if we define a small parameter, epsilon being the ratio of the inverse temperatures, simulation temperature and the target temperature, and we rewrite our Langevin equation, then it turns out that this controlled Langevin equation, already with the optimal control plugged in, because the optimal control is just generates a new friction, can be written in this form. And so if the matrix D, which is just a rescaled version of the original friction matrix gamma, satisfies this fluctuation dissipation relation at the correct target temperature, this is equivalent to the old friction matrix gamma satisfying fluctuation dissipation relation at the simulation temperature. Okay, so this doesn't look so fancy. Now, if we send epsilon to 0 and do a rescaling of time, it turns out that because we send the simulation temperature to infinity and keep the target temperature fixed, the invariant measure will be preserved for everything we do, and so for any value of epsilon. And it turns out that if we rescale time, the Langevin dynamics under this scaling becomes this one. So it has one of epsilons everywhere in place. And so if you have seen this already, this may look familiar, because this is exactly the scaling that you find if you take the overdamped limit of the underdamped Langevin equation. And if I send epsilon to 0 now, what happens is actually well known. So if we send epsilon to 0, then it turns out that the x component of this underdamped Langevin equation, which is mainly the component I'm interested in, because this is the component related to my positions and my potential B. This X component converges to the solution of the overdamped Langevin equation. What does this mean? So this means that if we make the temperature ratio higher and higher, we don't get an infinite speed up of the convergence to the equilibrium measure, but we just recover the overdamped Langevin equation. Okay, so that's a bit disappointing, but on the other hand, it's also good to know that there's no free lunch. Okay, and in fact, so for the overdamped Langevin equation that we get in the limit, the invariant measure still has the correct density e to the minus beta b at the correct target temperature. That's good, or good to know. How does the other case look like? So if we keep the simulation temperature fixed and send the target temperature to 0, then we observe again this concentration of measure phenomenon. So if the Hamiltonian has a unique global invariant measure, global minimum, then the measure will concentrate on this global minimum. If we take this other scaling in the Langevin dynamics, we get an equation of this form, and the only difference to the previous Langevin equation was that is that we have now 1 over square root of epsilon, where we had 1 over epsilon in the other case. So that's the only difference in these two situations. And so if we now send epsilon to 0 after doing the rescaling of time, what happens is that we don't converge to the overdamped Langevin equation, but we converge to a gradient system. That's also not so surprising because with the 1 over epsilon here, we got the overdamped Langevin equation with the 1 over square root epsilon here, which blows up much slower than in case 1. We get something where the noise doesn't survive the limit. So the noise doesn't appear in the limit equation anymore. And the limit equation is basically the underdamped Langevin equation without the noise. And this is a gradient system. And so this means that for small epsilon, the underdamped Langevin dynamics at these, so with this temperature separation and the control mimics a gradient system. And this is something that can be used to to use this Langevin dynamics at the 2 different temperatures to simulate something like a stochastic gradient descent, but now with momenta. So this is really an approximation of a gradient flow. Okay, so I will not speak about the proof because this is relatively standard, and you can either ask me for the details later on or read it in the archive paper. But the main point behind this is that I mentioned these 2 limits at the beginning: the ergodic limit t to infinity and the small noise limit epsilon to 0, or the temperature separation limit. And so what this shows is simply that these 2 limits do not commute, because the overdamped Langevin equation has the underdamped Langevin equation has an invariant measure e to the minus beta h that is always reached if I send t to infinity. However, if I send epsilon to 0 first, then, and my system has a global minimum, then I will collapse to this minimum. And if I now send t to infinity, nothing happens anymore. So I will never reach e to the minus beta h if I send epsilon to 0 first. So in this sense, these 2 limits do not commute. But as I said, so this can be used to use the Langevin dynamics in order to mimic a gradient descent algorithm. And before I conclude, I will just give you some examples to illustrate what happens. So the first example is very simple, just to get an idea of what is happening. So I consider a linear Langevin equation. So that's an underdamped Langevin equation, but it's for a quadratic Hamiltonian. So this means the equation is linear. And I can write it in this form. And the A matrix, well, has, so this anti-diagonal here is the usual skew-symmetric part. And this term is the friction part here. And so the A matrix is what you get from a quadratic Hamiltonian, assuming that all the other coefficients are constant. And the C matrix is the diffusion matrix, and you see this typical degeneracy. So there's no noise in the position part, but there's only noise in the momentum equation. And so gamma and K are symmetric positive definite matrices, and I assume that my modified fluctuation dissipation relation holds. So this is the fluctuation dissipation relation that guarantees that I sample from the correct invariant measure. And the invariant measure is in this case Gaussian, and it's Gaussian with the covariance given by the inverse of the Hessian of the Hamiltonian. So has a 1, so it's block diagonal, and it has 1 here because my mass matrix is equal to the identity, and has the inverse of the stiffness matrix that comes from the quadratic potential. And so that's the unique invariant measure, so it's Gaussian. And now I can study the equilibrium, so the convergence to equilibrium quite explicitly, because it has been shown by Anton Arnold and his PhD student that if you look at the speed of convergence and relative entropy, it's again exponential. So even for this degenerate system, and it's exponential with a rate that is given by the real part of the principal eigenvalue that is closest to the imaginary axis. So the interesting thing is that this convergence rate is independent of the noise. It depends only on the stiffness matrix A. And the explanation is, okay, the noise will make the distribution a bit wider, and it helps you to sample, but it also tells you have to sample over a larger part of the phase space. So the noise cancels at the end, and the convergence rate depends solely on the A matrix. Why is this interesting? It's interesting because it tells us how we can optimize our temperature ratio in order to get an optimal speed of convergence, because we can explicitly compute the eigenvalues of this A matrix in simple cases, and in more complicated cases we can do it under some assumptions. And it turns out that for example, for a one-dimensional system, which means so position and momenta makes it two-dimensional, so A will be a 2x2 matrix. In this case, the optimal bound for the speed of convergence, so this will be the Gaussian distribution we want to sample, and the optimal speed of convergence is a temperature ratio for the parameters that we chose of, I think, 1/2 or so. So this means that if the simulation temperature is twice as high as the target temperature, we get the optimal speed of convergence. However, so this temperature ratio, so this is true if K is 1 and gamma is 1, then we get this factor of 2. However, if K and gamma are different, we can also have the case that we have to use a lower simulation temperature. So in this case, even a lower simulation temperature may be optimal in terms of speed of convergence. So this is quite disappointing, right? Because it tells us that the original idea we had to just increase the noise in order to speed up the convergence is not universally true, right? I mean, so even in the simple example that has no metastability whatsoever, because it's a unimodal Gaussian distribution, it's not so clear what the optimal temperature ratio is. But so this was a good starting case, and we used this starting case to do some empirical studies. And so the other empirical study that we did was a bistable potential now. So this is now a nonlinear system where we have no possibility to optimize the temperature ratio analytically. And so in this case, we used a bistable potential coupled to a bunch of harmonic oscillators. So in this case, 100 harmonic oscillators. And we were interested in sampling the marginal of the first coordinate, because this is the coordinate that contains the bistability. And the invariant density is shown here. And we compared, so we played around a little bit and tried to empirically estimate an optimal temperature ratio, which in this case turned out to be equal to 5. So for the parameters we were using. And so in this case, so the red line here, so the red curve you see is the trajectory for the system simulated at the target temperature, and you see few transitions between the two wells at plus and minus 1. Okay, maybe so so if you look at the scales, so this goes from -20 to +20, but ±1 is really here close to 0 on this scale. And if we compare this to the underdamped Langevin simulation at the higher simulation temperature, which is 5 times the target temperature, we observe just more mixing of the first coordinate, which is the important one. And if we look at the empirical distribution, it also turns out that we get a much better approximation for a relatively short trajectory. But this is what we got from an empirical optimization of the temperature ratio. So there are cases in which this idea can actually be helpful. Then as a final example, I just want to bring back the idea of mimicking gradient descent to you. So we have been trying to find the minimum energy configuration of Lennard-Jones cluster. So if you remember this picture of a potential energy that I've shown you at the beginning of this Lennard-Jones 38 cluster, we've now considered a smaller Lennard-Jones cluster, which consists only of 7 atoms. And for the smaller Lennard-Jones cluster, we were trying to find minimum energy configuration starting from a very high energy configuration. And the idea was to use the Langevin equation with an extreme temperature ratio. So in this case, a factor of 100, but we do it the other way around. So we keep the simulation temperature fixed, being equal to 1, and the target temperature is sent to 0.01. And this means that the invariant measure will concentrate in the local, in the global minimum. And in this case, because of symmetry, there are several global minima, but we relax to the closest one, depending on the initial conditions. And it turns out if we compare the original simulation with simulation temperature equal to 1 and the simulation where we send the target the target temperature equal to 0.01. So this quickly relaxes to a very low minimum of this dynamics. So the interesting bit is if you compare this to the noisy simulation where we keep the target temperature equal to 1, this has more or less the same speed of convergence in finding an area close to the global minimum. However, I mean, it turns out we haven't found the global minimum yet because the stochastic simulation even finds a deeper minimum. But the fluctuations are much stronger, so it doesn't stay in this minimum, and only the simulation where we keep the simulation temperature small, the target temperature small, will stay in this minimum that is already very, very close to the global one. Okay, so with this, I want to conclude. And so this is now part 2 of my take-home message. So the message I want to convey was that one can use feedback control in order to accelerate the convergence to equilibrium, but there are limits. And so the limits are that, so probably it has to do with the fact that the asymptotic entropy production rate we are considering is not yet the right quantity to look at in order to get a good speed up. But I mean, the idea I think is very appealing to optimize the speed of convergence by adding controls to the system from a class of controls that preserves the invariant measure. And I just want to mention there are related results for the overdamped Langevin equation where people have added non-symmetric terms to the non-symmetric forcing terms to the equation in order to speed up convergence. But frankly speaking, I think their findings were also a bit disappointing. I mean, like in our case, because they found that if you add a non-symmetric part to the drift of the dynamics, then the speed of convergence is not decreased, which doesn't imply it's increased. But I mean, I would say they are non-negative results. So maybe that's a good way to express it. And but there, I mean, so I think the idea to use this 2-temperature dynamics in order to do something like simulated annealing is actually appealing. So you can really try to make an adaptive choice of this temperature, and wherever you think you've reached something that is close to a local or a global minimum, you can turn down the temperature and then let it quickly relax to a good minimum. But this is something we haven't really systematically tried yet. Okay, with this, I like to thank you for your patience and thank all my collaborators, and I'm happy to take questions.
Thank you very much, Carsten. And now, indeed, it's a time for questions. So